Say you want to know how long your morning commute really takes. You don't sit there with a stopwatch every day for a whole year. You jot down a handful of mornings. 22 minutes Tuesday, 31 Wednesday because of a detour, 19 on Friday.
And then, without even thinking about it, you tell your boss it's about 25 minutes, which is a massive leap of faith. You just took a tiny sample, summarized it in one number, and declared it the truth about all 250 workdays.
And that instinct, take a handful of observations and let them speak for the whole reality, is the heartbeat of today's lecture. We're going to make the whole samples and data analysis toolkit visual. Stem and leaf plots, histograms, the 5-number summary, the box plot.
The rule for the hour: no formula without a picture first. We'll see each idea in our heads before we ever touch a symbol, and then put the whole kit to work on a real restaurant's books. Let's go.
Here's the first image. You're cooking a giant pot of soup, a cauldron, and you want to know if it needs salt. You can't drink the whole pot, so you stir it well, dip a spoon, and taste 1 spoonful. That spoonful is your random sample, an independent, identically distributed draw. The stir well part is the independent and identically distributed part. Every spoonful fairly represents the pot. No scooping sludge off the bottom.
And the specific numbers in your spoon, little x1 through little xm. That batch is your sample of size m. The lowercase letters are just the values in hand.
Now, the whole cauldron, the population, holds the real truth. A true mean we call mu, and a true spread we call sigma. But you can't drink the whole pot, so those true numbers are hidden from you, forever. The entire job of statistics is to estimate them from your spoonful.
Let me put one concrete spoonful on the table. Flip a coin 20 times. Write a 1 for heads, a 0 for tails. There's the string. 14 ones, 6 zeros. Hold on to it. We summarize it on the next slide.
The first thing you do with a chaotic spoonful of numbers is boil it down to 1, the sample mean, x bar. Add up the values, divide by how many there are, m.
And here's a beautiful shortcut. When your data are just yes or no, ones and zeros, the average is the proportion of yeses. Same number, 2 jobs.
Watch it on the coin spoonful. Add 14 ones and 6 zeros. The sum is just 14. Divide by 20, 0.7. So x bar is 0.7, and it's 70% heads. One clean number summarizes all 20 messy flips. Same trick that turns website conversions or survey yeses into a single percentage. A sample isn't just a center, though. It has spread. For the center, we also have the median, the middle of the sorted values, and the mode, the most common value.
And for the spread, the workhorse is the sample variance, S squared. Picture all your data points as kids playing in a yard, and the mean is home base. Variance just asks, on average, how far from home base are the kids wandering? Measure each kid's distance, square it so everything's positive, and average. One catch that feels like a typo: you divide not by the number of kids, m, but by m-1. Why? The kids in your little sample naturally cluster a bit tighter around their own home base than around the true center of the whole neighborhood. So dividing by a slightly smaller number, m-1, inflates the answer just enough to stay honest.
On the coin sample, with x bar 0.7, the 14 ones sit 0.3 from home base. The 6 zeros sit 0.7 away. Square, add 4.2, divide by m-1, 19. And the variance is about 0.221, with a standard deviation around 0.47. Now, a real spoonful will live with all hour, the final exam grades of 60 students.
Center first. The 60 grades total 3,929, so the mean is about 65.5. The median, the student standing dead in the middle of the sorted line, is 71.5. And 2 grades, 74 and 80, each appear 3 times, so there are 2 modes.
Spread next. The range is 98 minus 10, 88 points. The standard deviation is about 21.
But park on something strange. The median is 71.5, a solid C-, half the class above, half below. Yet the mean is only 65.5, a full 6 points lower. The average student is somehow doing worse than the middle student. How is the center of gravity not in the middle? That's a genuine mystery, and it's completely invisible in the raw numbers. We have to draw a picture.
Easy first win. Just sort the 60 grades, smallest to largest, 10 to a row. Sorting is the gateway. Median, quartiles, box plot, all start here.
Find the median by counting to the middle. With 60 values, the middle lands between the 30th and 31st, and there they are, 71 and 72, in gold, straddling a row break. Average them, 71.5.
And once it's sorted, the modes pop out. The run of 374s and 380s in blue. 2 modes. The sample is bimodal. Quick but powerful shift. Every number we computed is one outcome of a random variable. Think of capital X bar as the recipe, the instruction, take a spoonful and average it. Little x bar, 0.7, is the actual meal you cooked this time. Same recipe, capital S squared and little s squared.
And that matters because every spoonful is different. I dip and get 3 carrots and a chicken chunk. You dip right after and get all broth and a potato. My grade sample mean might be 68, where yours was 65.5. So why trust any of them?
The law of large numbers. Flip a coin 10 times and 7 heads, 70%, is just luck. A small sample wiggles a lot. Flip it 10,000 times and 7,000 heads is essentially impossible. As the spoonful grows, the random wiggles cancel, and the sample summaries home in on the hidden truth. X bar marches to mu, S squared to sigma squared.
That's exactly why we call them estimators, trusted mathematical stand-ins for a reality we can't measure directly. We compute from the sample, we conclude about the population.
Time to draw. The first plot keeps every single value. Picture a tall filing cabinet with 9 drawers, 1 through 9. Those are the stems. A grade of 74 splits. The 7 opens drawer 7. The 4 is the leaf you drop inside.
File all 60 grades that way, and look at the cabinet. Drawer 7, the 70s, is absolutely stuffed with leaves. Stem 7, leaf 4, 3 times over, those are the 374s.
And here's the magic. Mentally tip that whole filing cabinet onto its side. The rows of leaves stick straight up like bars. You didn't do any math. The numbers drew themselves into a bar chart, which is exactly where we're going. Stand the cabinet up as a histogram. Each drawer was already a class, the teens, the 20s, on up. So just count the leaves in each drawer and divide by 60. There's the table.
And the bars are those counts. I've printed each leaf count on top so you can see the 14 leaves at stem 7 became the tallest bar. Now look at the shape the tipped cabinet reveals. A towering pileup in the 70s and 80s. Most of the class did fine, but stretching way out to the left, a long, thin tail. A few in the 40s, a couple in the 30s, and out at the far edge, a lonely 15 and 10. Hold that picture.
Because that shape solves the mystery, and the seesaw is the way to see it. Picture a playground seesaw. The median, our middle student at 71.5, is just a kid standing in the thick of the crowd. It counts heads and holds steady in the center, ignoring the edges. The mean is something different. It's the physical balance point of the seesaw. And basic physics says a couple of kids sitting way out on one end exert huge leverage.
And there it is. Those 2 students who scored a 10 and a 15 are sitting way out on the far left edge. Pure leverage, dragging the balance point down to 65.5, while the median holds with the crowd at 71.5. The long left tail dragged the mean down. The grades are skewed left, exactly what the histogram showed. Mystery solved. And the lesson? Never trust an average without checking whether a tail is dragging it around in the dark.
Drawing 60 leaves is a great exercise, but tedious. So we summarize the whole shape with 5 numbers: the minimum, Q1, the median, Q3, and the maximum. Picture taking the sorted line of students and chopping it into 4 equal groups, 15 kids each.
On the grades, min 10, max 98, median 71.5. Q1 is the median of the lower half, 54.5. Q3 the median of the upper half, 80.5. The interquartile range, the IQR, is Q3 minus Q1, 26 points, the width of that middle bunch.
And the strip shows it. The gold band is the middle half of the class, 30 students, squeezed into just 26 points. 5 numbers and you've got the whole shape. Draw those 5 and you get the box plot. and sports imagery builds it. The box is the middle 50% of the pack, the ordinary players on the field. The median is the line inside. Then the fences are the out-of-bounds lines. Step 1.5 IQRs out from each end of the box. Why 1.5? John Tukey worked it out. For normalish data, that width captures about 99% of your typical points. The whiskers reach out to the farthest players still in bounds, and anyone past the line, out in the parking lot, is an outlier, drawn as a lonely dot.
On the grades, the IQR is 26, so 1.5 times that is 39. The low fence is 15.5, the high fence 119.5. Our 10 and 15 sit past the low fence, flagged as dots in the parking lot. The whiskers reach the farthest ordinary grades, 17 and 98. Long left whisker plus low dots, the left skew, one more time.
Now, the instinct everyone has, an outlier is ruining your neat data, so just hit delete, right? Never. The box plot is a diagnostic, not an eraser, and there are 3 honest reasons to flag. The strongest, the point may be a different kind of thing that snuck into your sample, a different population entirely. Quarantine it and study it. Don't delete it.
Second, and we just saw it on the seesaw, one extreme point can hijack the mean and the variance. Those are non-robust summaries. The median and IQR barely flinch, so when the mean and median disagree, the box plot is an alarm bell. Your average has been compromised.
And third, it's a data quality check. Maybe somebody typed a 10 where they meant 100, a recording error worth catching. Or it's a sign that an assumption behind some later test is shaky. Flag, investigate, decide, never just erase. Let's earn all of this. Babcia's Pierogi Kitchen, a family restaurant, has a burning question. Is an order that comes through a delivery app worth as much as a direct order from someone who walks in or calls?
On their business model canvas, the shaky block is channels, and the risky assumption is exactly that. An app order is worth about as much as a direct order. The data plan: record every order for a week, split by channel. If you're doing the class project, that is your milestone 2 brief: a flagged assumption, a number to measure, a sample to collect.
So they sampled 20 direct orders and 20 app orders. There's the week.
And before we compute, one number is screaming off the table: that $150 direct order. Keep your eye on it.
Run the summaries on each channel. There's the table, center, spread, the 5 numbers, side by side.
And the first clue is right there. The op channel is wonderfully calm. Mean 2170, median 2150. The seesaw's perfectly balanced, no leverage. But the direct channel is chaos. The median order is 3250, while the mean is a scary 3825. Something's sitting way out on that seesaw.
If you trusted the averages alone, you'd run to the owner yelling, direct orders are worth almost $17 more. Ditch the apps. That's a big, expensive claim. Before anyone believes it, picture the data. 2 box plots, 1 axis. Instantly the story's clear. The app box sits well below the direct box. Typical orders around 2150 versus 3250. And out on the far right, all alone past the fence, that $150 order flagged as a dot.
It's the billionaire in the diner. Picture a quiet diner where the typical customer has $10 in their wallet. Then a billionaire walks in and orders a coffee. Average the wealth in the room, and suddenly the average customer looks like a multi-millionaire, but the median wallet barely moved. That 1 point hijacked the room. And Babcia's 150 wasn't a really hungry guy. It was a catering order, an office party, a completely different kind of sale. So we don't delete it, we quarantine it. Catering is its own business. Pull it out, and the ordinary direct orders average about 3240, lining right up with the median. The seesaw levels out. The mean is honest again.
And you don't have to do any of this by hand. The free GeoGebra calculator suite does the whole toolbox at once. Type the 20 direct orders into a column, ask for mean, median, quartile 1, quartile 3, and it returns 3825, 325, 265, 40. Then the box plot command draws the picture and highlights the billionaire for you, a dot at 150. Exactly our hand results, in seconds. So what can Babcia's honestly conclude? Set the catering order aside as its own kind of sale and compare ordinary orders mean to mean. about 3240 direct versus 2170 app, a true gap of roughly $11, not $17, and the boxes barely overlap, so the gap runs through the whole distribution. For a small business, 11 versus 17 is a huge difference.
But here's what we cannot say yet. Remember the flaw in the soup analogy? Every spoonful is different. Track a different week and the averages shift. So the question hanging over everything, exactly how much does a sample mean wiggle from week to week?
And that wiggle is the whole basis of statistical inference, knowing how much an average is allowed to bounce before you hit the panic button. That's next lecture's Central Limit Theorem and the formal test of two means in week 4, the same path your own project takes, from a data brief to a defended decision. Let's step back and look at the journey. We tasted a spoonful of soup to judge a hidden pot. We boiled it down to a mean. We built a filing cabinet of grades and tipped it on its side to reveal the shape, used a seesaw to see how a heavy tail drags the average around, and painted out-of-bounds lines on a field to catch a billionaire hiding in a pierogi diner.
And if you synthesize all of it, you get a genuinely powerful lens. A mean is a measure of physics. It cares about weight, distance, and leverage. A median is a measure of democracy. It only counts votes, head counts. In a world full of billionaires and outliers, when you want to know what's typical, trust democracy, not physics. The one open question. The data looks convincing, but a different week gives a different X-bar. How much does it wiggle? That's the sampling distribution.
And answering it is next time, Lecture 13, the Central Limit Theorem, and then the chi-squared and t-distributions behind real inference. See you there.